Hi there everyone, Mr. Godfrey here. In this video we're going to be going through the Physics Newtonian World June 2011 past paper. And if you haven't done so already, then go to the description for this video and follow the links so that you can open up the question paper and the mark scheme, because it will be really useful if you can refer to the question paper and the mark scheme while we're going through this video. So if you haven't got those open already, then pause this video and get them open. If you have got them open already and you're ready to go, then let's go. So first question, we need to state Newton's first law of motion. Now for that we needed to say something along the lines of an object will remain at rest or at a constant velocity unless acted on by an external force. Now, most of us did quite well with this, but there's a couple of places where we can slip up with doing this question. So let's bring in our first model answer, and then we'll take a look at some of the problems that can occur when we're answering a question like this. So bringing in our first model answer. This candidate has said that an object will continue travelling at a constant speed or remain at rest unless acted on by an external force. Now that's not a bad answer, but it hasn't quite hit the nail on the head. The reason being is because they've used this term constant speed instead of a constant velocity. Now the reason that we can't talk about it being a constant speed is you can have something that's at a constant speed, but its velocity changing. An example of this is circular motion. When something's undergoing circular motion, it may well have a constant speed, but because it's undergoing circular motion, its direction is constantly changing, therefore its velocity is changing. And as a consequence, it's not following Newton's first law of motion. So when we're saying this, we need to say it will remain at rest or a constant velocity to make sure that our definition is absolutely spot on. Second question, we're defining a Newton. The definition of a Newton is the force required to cause an object of mass 1 kilogram to accelerate at a rate of 1 meter per second squared. Most of us did quite well with this one, but there's a couple of times when we can go wrong. Let's look at an example of where someone's gone wrong with this question. This candidate has said that a Newton is the force of a 1 unit mass accelerating at 1 meter per second squared. Now this candidate got really close with this one, but they didn't quite get it perfect. The problem that they had was when they were talking about the 1 unit mass. Now we've got to define what our unit of mass is. So what we could say is a Newton is the force of a 1 kilogram mass accelerating at 1 meters per second squared. More precisely, we could say instead of the force of a 1 kilogram mass, we could say the force on a 1 kilogram mass accelerating at 1 meters per second squared. So with these definition questions, it's really important that we get the words in the right order, because mark schemes are really strict when it comes to using keywords in definitions. So moving on. Part B. In Part B, we are talking about a jet plane. And whenever you have any kind of questions about a jet plane taking off, it's most likely to be a SUVAC question. And the way that we deal with a SUVAC question, we prepare our page ready to answer the SUVAC question. So S, U, V, A, and T. We write down what we've got and what we're trying to look for. So, have we got a distance? Nowhere in the questions it say that we've got a distance. So that bit we can't fill in. This bit is 0 meters per second. And the way that we know that is it's accelerating from rest. So that's our U there. Our V. It accelerates to a velocity of 55 meters per second. So that is our V there. Our acceleration, we haven't been told. And the time that it takes to accelerate that is 2.2 seconds. SUVAC questions at A2 level should be being dealt with quite confidently. So I'm not going to go through the details of this one, but if you didn't quite get that one right, Then pause this video and spend the next few moments just going through that, checking the mark scheme, making sure that you're getting it right. So let's move on to part C of this question. So we're talking about the same plane, and the jet plane, first of all, it describes a horizontal circle of radius 870 meters, and it's got a constant speed of 120 meters per second. So let's just take a look at what we're talking about here. Here's a little picture that I made of what this aeroplane is doing. So here's our aeroplane here, and it's a horizontal circle. So what we're looking at is a bird's eye view. We're looking down upon this aeroplane, and it's describing this circular path here. And our first question is we need to state the direction of the horizontal force acting on the plane. Now, horizontal force is going to be, let's change color, it's going to be, let's change color, it's going to be this force here. It's going to be a force directed towards the center of the circle. So anything in circular motion, there's a force exerted on it towards the center of the circle. We also need to calculate the magnitude of this horizontal force, and it's a centripetal force, so you need to use this equation for centripetal force. And I've given you the solution underneath. So if you didn't quite get that one right, then pause it, go through the solution, and then pick us up in a moment. After we've done our horizontal circle, our plane, it changes what it's doing, and it starts describing a vertical circle. And this is the sort of thing we mean by a vertical circle, where it's kind of doing a loop-the-loop. That's how I've interpreted this question. And we are being asked a couple of things about this particular question. So we are being asked, state and explain at what point in the circle this weightlessness may occur. So what we're thinking about is, what we're looking for is the point in our circle that the downward force caused by gravity on the pilot is the same as centripetal force. So let's just define our downward force. So our downward force is going to be something like that. And we're looking for when the weight of this is equal to the centripetal force. And in this case, the centripetal force is here. So what we're looking for, and let's just label that, I don't know, CF, the centripetal force. So there's our centripetal force. We need that to be the same as the weight. Now, at the moment, when it's at this position here, it's not the same as the weight. So let's bring another aeroplane in. Let's see what our centripetal force is when it's here in its orbit. And let's put our centripetal force in there. And it's going to be something like that. There's CF, the centripetal force, but it's still not looking like our force here. Let's try a different point in its orbit. And this time, we're going to try the top. And let's take a look at what our centripetal force is doing here. So here, directed towards the center of the circle. Label it CF. And here, as we can see, the centripetal force is directly downwards, and the weight is directly downwards. This is the only point in the circle where this is going to be true. Let's just move it on one more, wherever we put our aeroplane. So here it is, and here towards the center of the circle. But no, it's not looking like our force there. Let's put it down the bottom. And here, well, it's towards the center of the circle, so it's along the right line, but it's not quite, it's in the wrong direction. So this is the answer that we were looking for here. So back to our question, wherever it's gone. Yep, here it is. So our question was saying, state and explain at what point in the circle weightlessness may occur. And what do we need to write for this? We need to write at the top of the circle, at the top. Now, we've only partly answered this question. So here we've probably got 1 mark because we've stated it. We need to now explain. We need to explain how this weightlessness can occur. We can explain this point as well by saying that it's at the top, and we also need to say that the weight is equal to the centripetal force. When we're talking about the weight, we also need to include that it's the weight of the pilot and the centripetal force on the pilot. So there's your answer there. We also need to calculate the speed at which this weightlessness can occur. So in this situation, we need it when the force on the pilot, which is their force is their mass times their acceleration. Or well, so this is the. So we need to calculate the speed that the plane, at which this weightlessness occurs. So the speed that it's going to be, to go about finding this, we need to first of all find the force. The force that's due to the weight. So where we're saying force here, we're saying that this is the force, and it's the force of the weight of the aircraft. Okay? And force is equal to mass times acceleration. We also need to say this is what's representing the weight here. We also need to know the centripetal force, and centripetal force is F equals mv squared over r. And we want it where the weight and the centripetal force are the same. So we want it so that ma equals mv squared over r. So we can do a little bit of cancelling here. So here we can cancel the masses. So we just leave left with the acceleration. So here's centripetal acceleration is v squared over r. And now let's try substituting a few of the numbers. So here our acceleration is acceleration due to gravity, 9.81 meters per second squared. And we're trying to find v squared here. And our radius of our circle here is 1,500 meters. So rearranging for v, what we end up with is 120 meters per second. So that's how we do that part. Next question. Next question is all about simple harmonic motion. And whenever we're asked to define simple harmonic motion, we need to make sure that we're getting things right. And there's normally 2 points that we need to make. First point is that the force, and when we're talking about the force, a better way of saying it is instead of just a force, we need to talk about a restoring force. So the restoring force is proportional to the displacement from equilibrium position. I'm just going to write EQM for equilibrium position. Okay, that's your first mark. restoring force is proportional to the displacement from the equilibrium position. 2 marks available though. So for our second mark, we need to say that the restoring force and the displacement from the equilibrium position are opposites. So that displacement and force are in opposite directions. There's our second mark. So 1 mark for saying the restoring force is proportional to displacement from the equilibrium position. Our second mark for displacement and force are in the opposite directions. So we next need to talk about the following statements about an oscillating mass on a spring. So we're going to go through each one and we're going to state whether they're true or false or not. So over to our first question. We need to say let's have a look at number 1. The period of oscillation is constant, and for any system undergoing simple harmonic motion, we'd say this is true. Period of oscillation is constant. There's a constant time period. The frequency is the same. It's the same number of oscillations per second. We can say that's true. The net force on the mass is equal to its weight. Now that is not true. If, for example, with our mass in this particular question here, if this had like a mass, for argument's sake, of 1 kilogram, it would have a weight of 9.81 newtons. So this is its weight that we've just worked out, and our question or our statement is that the net force on the mass is always equal to its weight. So in other words, the total force is always equal to 9. In this situation, it's always equal to 9.8. Well, that doesn't quite make sense, because sometimes there might be a force pulling upwards, and with this upwards force, it cancels out some of the weight, and this upward force isn't always 9.8. So it's false to say that the net force on the mass is equal to its weight. Let's take a look at number 3 now. The acceleration of the mass is at a maximum in the midpoint of the oscillation. Now let's have a look at our diagram here. So if it's at a midpoint in its oscillation, so here we're going to say, well, this is our spring at full stretch. So this is where it's being pulled to a maximum extent there. Here is where it is at a minimum. So this is when it's at a minimum. This is when it's right at the top. When it's gone down, it's bobbed back up again. And this is when it's at the midpoint. So there's your midpoint, roughly about there. And what our statement is saying is that the acceleration is maximum at the midpoint of the oscillation. Now, if we put our mass here at the midpoint of our oscillation, that's its equilibrium position. That is where it likes to rest. So if we put it where it likes to rest, it's not going to move. Therefore, it's not going to accelerate. So the acceleration of the mass is maximum at the midpoint. Absolutely false. The velocity of the mass is proportional to the displacement. Velocity of the mass is proportional to the displacement. And so what that is saying is that let's have a look at our situation here. This is our mass at full stretch. And here, when it's at full stretch, it's turning around and it's about to come back the other direction. So here is where we've got our velocity is equal to 0. Here, we've got that the velocity is also equal to 0. So that's when it gets to the top and it's about to come back down again. Here, this is where V is at a maximum. So there's your V max point. And what are we saying? Our statement says that the velocity of the mass is proportional to displacement. So that's saying that as the velocity is bigger, the displacement gets bigger, or vice versa. The displacement gets bigger and velocity gets bigger. Now here is our the maximum displacement here. So here we've got maximum displacement here we've got minimum displacement. And what we can see is that when at maximum displacement and minimum displacement, velocity is 0. So as displacement from here to here gets bigger, velocity gets smaller. And from here to here, as displacement gets bigger, velocity gets smaller. So in this question, velocity is proportional to the displacement. Absolutely not true. And for this one, there were 2 marks available, and we got 2 marks for 4 marks out of 4, and we lost a mark for everything that we got wrong. So if we got 3 out of 4, then that would be 1 mark, and we would get no marks for 2, 1, or 0 out of 4. Okay, so that's how you were marked up on with that one. Now this is quite an involved question, and so let's take a quick read through it. The student wishes to investigate whether the period of oscillation of a simple pendulum is constant for all angles of swing. So in other words, they want to find out if I pull something really, like with a pendulum, if I pull it really far up, will it swing the same number of swings per second as when I pull it just a little bit? So how could they find that out? We're being asked, describe how the student should carry out the investigation. Include the following in your description. So we've got 4 parts that we need to include in our description, and we're just going to go through each bit one by one. Now there's an old phrase that a picture can say 1,000 words. And so for this one, we're going to bring in a answer that students done, and it's a sketch of the apparatus that they might use. So what we would need to do is we need to take this representing our pendulum. Students labeled it there, and they've said, well, we need to swing it up here. They've labeled the angle of swing. They've told us how they're going to measure that angle. They've included a timer. They've labeled the timer. They've also included a set of light gates in there. So we'll get onto how the light gates are involved a little bit later on. So this is the sort of sketch that we need. Just simple sketch of what is going to be going on. Doesn't need to be fancy. Just needs to be a nice, clear description of what equipment you'll need. Second part we need to look at is details of how the measurements would be made. So how would we take measurements to find out whether that angle of swing is the same for all angles? So I think first thing that we needed to do is we needed to take our measurements. Okay, so we needed to record the period for different angles. So record the period for different angles. So record the period for different angles. We also needed to mention something about how we would record the measurements. And we could have either, like this candidate has made it explicit by saying that we needed a protractor and some sort of timer. But if you didn't include that in your diagram, then you would say that a protractor measures the angle and that a timer measures the time. Once you've said how the measurements would be made, another part of this question was to explain how you would use these results to form a conclusion. And the main way in science that we use results to form a conclusion is we might plot a graph. And we're plotting a graph of the angle against, actually, no, change my mind there. We're not going to do angle against time, because that angle in this case is our independent variable. So we're going to plot a graph of the time against angle. Time against angle. And to draw some sort of conclusion, we need to say that we've compared. time to angle. So some sort of mention there that we're comparing the time against the angle, and then we're looking to see if they're the same. So compare time and angle to see if, and what we check in to see whether it is the same, we need to see that the time is the same. Also, we need to also say any likely problems that might occur when we're doing this experiment. And the most likely problem that might occur is that the angle of the swing decreases during the timing of the swing. So that's something that we were looking for with the mark scheme, according to the mark scheme there. So the angle of the swing decreases. So that's like your major problem there. We also needed to identify a solution. So if the number of swings is decreasing over time, then we need to make sure that we measure that angle in just one swing, so that we're not changing the angle over and over again. So we pick up the time in that first swing before it's had a chance to slow down. Way that we can do that is to use some light gauge, some sort of data logger, or video what's going on. So video the experiment with a timer in the video, and then we can just go back and pause the video. So there are your answers summarized. If you need to look at this in a little bit more detail, then pause the video and take a look at the mark scheme. It's important that you know why you got marks for this and why you missed marks for it. In this next question, we need to define gravitational field strength. And the answer to this one, that should be in your kind of bank of definitions that you're building up in your head there. And what we're looking for here is that gravitational field strength is the force per unit mass on an object in a gravitational field. In a gravitational field. And something along those lines will get you the mark there. If you've written something else and you just need to double check that, then pause the video and take a look at the mark scheme. Let's take a look at this next one then. So our next one, the table shows in modern units information that was known to physicists at the time of Isaac Newton. So back in the time of Newton, we knew things like, what have we got here in our table? We've got the distance r from the center of the Earth. So in other words, we knew the size of the Earth, and we knew the size of the moon's orbit. Okay, so this number here is how far away the moon is, and this number here is the radius of the Earth, effectively. What else did we know? We knew the gravitational field strength G at the surface of the Earth. So this is what we know as the acceleration due to gravity. And also at the moon's orbit, this is what our value of G is. So remember that the gravitational field strength decreases the further you get away from an object. And by the time we're as far away as the moon is, this is what the Earth's gravitational field is. Now, this really, really clear. We've got to be really, really clear that this isn't the G on the moon. So if you're thinking that that's the gravitational field strength on the moon, then we are mistaken. That is not what we're looking at here. So it's really important that we get those points understood. So we need to state the relationship between gravitational field strength and distance r, and we need to verify this relationship. So let's do this first little bit first. So first little bit that we need to do, state the relationship between G and r. And the relationship that we're looking for is we can write something like this. We can write G equals big G m over r squared. Okay, so that's one answer that we could have given. Let's just neaten this up a little bit, because that's not particularly clear. That's one way that we could have started this. We could have also said that G is proportional to 1 over r squared. Having done that, we also need to verify this relationship as well. Where's my pen gone? It's still there. So we need to verify this relationship. So we need to say, well, whether it's true or whether it's false. And the way that we can verify this is using the data up here. So what we need to say is that, well, here's G. So this column is our G, and then this is our R. So what have we got? We have, and if we've got something proportional to each other, then when we say G times R squared, that should equal a constant. Okay, so let's try that. Let's try our G. So let's do this first row. Let's do it for the surface of the Earth. Okay, and at the surface of the Earth, our G is 9.8, and let's times it by R squared. 6.4 times 10 to the 3, but that's squared, and for that we get 4.0 times 10 to the 8. We also need to do it for this second row as well. So we need to do it for the moon's orbit. So G at the moon's orbit is 2.7 times 10 to the negative 3. And we need to multiply that by the R. And well, we've got 3.8 times 10 to the 5. That's all squared though. And for that one, we get 3.9 times 10 to the 8. Okay. What have we got so far in terms of marks? We've got a mark for doing this bit. A mark for doing this bit, because that shows that we're verifying it. And we also get our last mark for comparing these two. So we need to make some sort of comment about G R squared for Earth's surface. It's similar, or in the same sort of area as for Earth is similar to G R squared at moon's orbit. So that's our third mark there for making some sort of comparison. Next question. We need to show that the mass of the Earth is this. So this is a pretty straightforward question. So we need an equation that we can use for this is we're told what G is earlier on in the question, little g. So we need to say big G m over r squared. So we came across that over here, and then we're going to use that here, and we're going to rearrange to solve it for m. Okay, so for this one here, m is G. We need to bring this one over here, so it's G r squared over big G. Let's do our substitution, 9.8 times, and then this, well, which R are we using? We're using R at the surfaces of the Earth, because that's where this is the value for G for. So we, what do we get here? We get 6.4 times 10 to the 3, and that bit squared. And we divide that by the universal gravitational constant, which is 6.63 or 6.67. I always get that and Planck's constant muddled up in my head. It's 6.7 there, times 10 to the negative 11 there. And we should get an answer of 6 times 10 to the 24 there. For the final part of the question, we need to determine the mean density of the Earth. And when we're talking about the density, it's got the symbol rho. Density is the volume divided by the mass. And that gives us the number of kilograms per meter cubed. So first thing that we need to do, we need to find the volume. Now, the Earth we can approximate as being a sphere here. And when we're talking about the volume of a sphere, what we're talking about is the volume is the 4 pi r cubed over 3. So that's our formula for the volume of a cube. So let's find the volume of the Earth, 4 pi, and our r. What's our r here? Let's just flick back to our table. R here is this, and I've just realized I've made a bit of a mistake here. So I just realized that I've made a mistake in that I've said that in this part here that it is 6.4 times 10 to the 3. I've made a mistake there because I haven't taken into account that this is kilometers. So it's 4 times 10 to the 3 kilometers, but it's 6.4 times 10 to the 3 kilometers, but it's 6.4 times 10 to the 6 meters. So apologies for making that mistake, everyone. So let's just change that there. And again, here, it's not 3.8 times 10 to the 5, it's times 10 to the 8 meters. So a massive mistake I've made there. So often we call that a power of 10 error. That's what we should have done there. Anyway, glad that I spotted that before, or hopefully you spotted it before I did. But anyway, we're back on track. So we need this in number of kilograms per meters cubed. So I'm not going to make the same mistake again. So we're going to times that by 6.4 times 10 to the 6. But that times 10 to the 6 is all cubed. And then we divide that by 3. So here's our volume of the Earth. And our volume of the Earth is 1.1 times 10 to the 21 meters. So there's our volume, and then we just take our 1. So we take our 1.1 times 10 to the 21 meters, divide that by the mass of the Earth, which is 6 times 10 to the 24. And what do we get for our density? We should have a number that is something along the lines of 5,500. So after a slightly embarrassing question number 3, let's just get straight on to question number 4. So in this one, our pencils come out. So we need to make sure that we're writing down our keywords absolutely perfectly. And here, what we're looking for is that the energy, we're looking for the thermal energy required to change a solid into a liquid. Now, when a solid goes to a liquid, we call it melting, but when it's the opposite way around, when it goes from liquid to the solid, then we say it's the latent heat of fusion. And this is the word, one of the words that we need to spell right. F-U-S-I-O-N, latent heat of fusion. Okay? And when we go from a liquid to a gas, it's called vaporization. So let's spell this one correctly. V-A-P-O-R-I-S-A-T-I-O-N. latent heat of vaporization. There was one exception that I could make to the spelling of latent heat of vaporization, and that is if we use the Z instead of a S there. Little mistake that people were making is we were thinking that vaporization is linked to this word here, so vapor, which is O-U-R, but when we spell vaporization, we don't use the U. So if we missed out on that mark because of our spelling, then that's something that we need to sharpen up for next time. This next question was a question about people overfilling their kettles. Fairly straightforward question. So I'm not going to go through the answer to this one, and I'm just going to bring in a model answer. So this really nice answer that we've been given here. We are told that the energy needed is the mass of whatever we're heating up times the specific heat capacity times the temperature change. There's the mass there, there's the specific heat capacity, and there's the temperature change. There's the calculation, there's your final answer there. So really nicely laid out answer there. Really good bit of physics there. So for this one, we need to state and explain two reasons why the actual quantity of energy required to warm the water to 1 degree Celsius is greater than the estimate in part I. So we're starting to think about what else is being heated up. So let's bring in our answers, because there's all sorts of things that we could have written for this one. So let's bring in our answers, and then we'll take a look at them. So here are the answers that we were allowed. And there are 2 marks available, and we could have used 2 points from this list. So we could have said that some heat is used to heat the kettle. We could have said that some heat or energy is lost to the surroundings, air, or the environment. Now, the surroundings could include the table that the kettle's on. They could include the wires that go towards the kettle. They could have been the air around the kettle. They could have been objects near the kettle. So when we're thinking about things in the environment, that's what we're talking about. So we need to say some heat, or we could have said some heat is lost to the kettle, lost to the surrounding air or environment. Some heat is also used to boil water before the kettle switches off. So sometimes your kettle carries on bubbling after it's finished heating it up. While it's bubbling, all it's doing is evaporating some of that water. So think back to our last question about latent heat of vaporization. That energy is just being used to evaporate the water. Okay, so it's not being used to change the temperature of the water. There were a couple of exceptions that I wasn't allowed to say. So I wasn't allowed to say, if you said some heat is lost, I'm afraid that wasn't specific enough. So you must have said how and where. So I wasn't allowed to accept the kettle is not 100% efficient. So if you mention something about efficiency, I think you're kind of right, but I don't think you're being specific enough. And another thing is we weren't allowed to say that energy is lost as heat as sound. Again, not specific enough. I want to know exactly how it's lost. So for this next one, this one wasn't done greatly, and quite a few people missed out on marks here. So let's bring in our solution. So what did we need to know? We needed to calculate in kilowatt hours the average annual energy wasted by boiling too much water. So to do this, we needed to find out how many joules were in 1 kilowatt hours. So in 1 kilowatt hours, so when we're thinking about things like this, we are thinking about, well, kilowatt hours is a measure of energy and joules is a measure of energy. But we need to know how many kilowatts or how many watts in a kilowatt and how many seconds in an hour. So 1,000 watts in a kilowatt and 3,600 seconds in an hour. Therefore, 3.6 times 10 to the power of 6 joules in 1 kilowatt hour. And this is the amount that's wasted in a year, the number of joules that's wasted per household in a year, And we need to say, well, how many kilowatt hours is that? So you take that number and divide it by the number of kilowatt hours. So there was your solution for that one. Next question. We're looking for three assumptions that are made based on the kinetic theory of gas. Now, I'm not going to go through them one by one. There's a nice little summary in your textbook. So let's just bring that in. And what we're looking for is three answers from the following list. So I'll just give you a moment just to pause the video so you can go through those. So let's take a look at this next one. We need to calculate the change in momentum of this particle, this molecule, as it collides with the face here. So what we have got here is something that changes velocity. As it's going this way, it's got a particular velocity, particular momentum in this direction, then it changes direction, and then it's got a momentum in the opposite direction. So let's calculate the momentum. Well, to calculate the momentum, so we're looking for the change in the, I'm going to just use momentum there. So mom for momentum is the momentum after minus momentum before. So let's take a look at what it was before. So our momentum before, well, what is our momentum? It's the mass times the velocity. So there's the velocity, there's the mass. So our momentum before was mass times velocity, 4.8 times 10 to the minus 26 times 500. Okay, that's our change in momentum there. Or that's our momentum before. Our momentum after, that's our first bit. Our momentum after, we have to be very, very careful when we do this. It's still the same mass. Particle hasn't, 1.8 times 10 to the minus 26. Our mass hasn't changed, but our direction has. So it's no longer going 500 meters per second. It's now negative, or I guess, negative 500 meters per second. Let's put that within its own brackets. And of course, that negative inside the brackets makes that a plus. So it's actually twice whatever its momentum was before. It's the change in momentum. And what answer did we get for that? 4.8 times 10 to the negative 23. So that's the answer that we should have got there. So to answer this next one, calculate the number of collisions made with the face in 1 second. We need to go back to good old-fashioned, that the speed equals distance over time. And in this case, our time is 1 second. And we want to know, and we've told it speed, so we want to find out the distance. We want to know how far it can go in 1 second. So if we flick back to our diagram, this particle is going to and fro, but it's going 500 meters per second. The width, one of the edges of our box here is only 0.2 meters, so it's going 500 meters a second. So we need to know how many times it can make that journey, how many times it can hit box side X in that amount of time. So it's got to go 0.2 meters there, 0.2 meters back, 0.4 meters. So in other words, how many times can it do that in 1 second? And so what we need to do is we need to do 500 divided by 0.4, and that should give us 1,250. So it goes to and fro 1,250 times a second. So that gives us our answer here. 1,250. Calculate the mean force exerted on the molecule by face x. So we're trying to find the force of something. So the force, and what we could use here is the change in momentum again, divided by the time. So our time here is 1 second, and the change in momentum is 4.8 times 10 to the negative 23. So we found that out a couple of questions ago when we did this bit, but that's not our full answer. We're forgetting the fact that that happens 1,250 times a second. So in this 1 second it happens that many times. So that changes our answer slightly and makes it a bigger force. And what we should have for that one is that our force is 6 times 10 to the negative 20. And we need to state the force exerted on face x by the molecule. And what we're looking for there is that we need to say that it is the same as whatever here. So whether you got this answer right or wrong, it needs to be the same as in part I. And the reason is when one object exerts a force on one object, that object exerts the same force back. So it's Newton's third law of motion because of Newton's third law there. Next question. A single molecule in the box is replaced by 3 moles of air at atmospheric pressure. Now there are 6.6, no, I'm getting my constants muddled up again. It's 6.02 times 10 to the 23 molecules per mole, so the number of molecules in total is Avogadro's constant just times 3. And that gives us 1.8 times 10 to the 24 molecules there. So just why the pressure exerted by the air on each of the 6 boxes is the same. Now, answers that we could have had for that is that we needed to say that there was a large number of molecules and we needed to say that they were moving randomly. Next part, the temperature of the air inside the box increases. Explain in terms of the motion of the air molecules how the pressure exerted by the air will change. So as the temperature increases, molecule speed increases. The effect that this has on the pressure exerted on the box, well, it will cause the pressure on the box to increase. And the pressure on the box increases due to the particles moving faster. They're going to be making more regular impacts with the side of the box, and they're going to be moving at a faster rate. So more regular impacts or more regular collisions, you might have said, and they are happening at a faster rate. Okay, in our final question, we need to draw the graph of the product of the pressure and volume and of the absolute temperature. So what our graph should have looked like is a straight line through the origin. And we needed to state what the gradient of this was. So if we take PV equals NRT, and if we turn it into Y equals MX plus C. Our PV is our Y here. Our M, our X, is the T. So our M is going to be NT. R. So that is our M there. That is our X, and that, well, the whole thing is our Y, and then of course our C is 0 here. So in answer to our question, state the gradient of this is N R. And the final question, we are taking we're taking 1.5 moles of an ideal gas, and its temperature is minus 40 degrees Celsius, and we're told its volume 2.4 times 10 to the negative 2 meters cubed, and the gas is heated at a constant pressure, and we need to find the new volume. So whenever we've got a question like this, we find P1, V1 and T1, P1, V1 and T1. So this is the pressure, volume and temperature before, and they need to equal the pressure, volume and temperature after. So what's our P1? What's that? P1, we'll just call it P because we're told that it's at a constant pressure. So that must mean our P2, it's going to be P as well. And our V1 is 2.4 times 10 to the negative 2. And our V2 is, well, it's what we're trying to find out. T1 is, well, minus 40, but it's minus 40 plus 273 Kelvin. So that's going to be 233 Kelvin. And our temperature that we finish with is 250 plus 273, and does that give us ends in a 3? That's going to be 2 and 4, 2, 3. So P before and after, they're going to cancel out here. So what we're looking for is 2.4 times 10 to the negative 2 divided by 233, and that's got to equal whatever our volume is over 4 to 3. And solving this for V, what should we get? 0.053, and calculate the value of P. So we need to use P, V equals N R T. So we're looking for P, so we need to say where it's 1.5 moles, so that's that bit there. R is 8.31, and T, well, it doesn't matter whether we use the temperature before or the temperature after, as long as our value for volume is consistent with that. So let's use the volume after, 0.053, and what do we do? No, we don't do that, we use 4, 2, 3, and then we divide the whole lot by 0.053. You could have used this value for the volume and this value for the temperature, doesn't really matter. But as long as you use this value for volume and that value for temperature, rather than this one for volume and this one for temperature. So as long as they're either before and after, or before or after, doesn't really make an awful lot of difference. And our final answer for that one is 1.21 times 10 to the 5 pascals. So that's the end. If you've got any questions, then come find me or drop me an email. Other than that, hope you found this useful.